Hello, how's everyone doing? Today we want to continue the data mining topic. And the slides that I'm going to use is from Stanford again. So get rid of this. Okay. So let's have a look at this interesting problem. Suppose that we go on a vacation, we take this photo, but the roof here destroyed the picture. So we want to see if we can repair it using similar images. So the idea is basically, can we remove that part of the photo and replace it with something from a potentially similar image, right? So the idea is to look at a set of images, find similar ones, and from those you repair that photo. Okay. So this is what we want to do today, finding similar items. If you want to do this, and we have a data set that contains only 20,000 images, these will be the top 10 most similar images to the original one. You can see that really none of them is that similar, right? But if you do the same thing, but this time we search in a data set that has 2 million images, we will find many images that are pretty similar to the target photo, and we can actually repair it, right? So the problem that we want to look at today is finding similar sets, right? Or in another word, finding near neighbors in high dimensional space. Examples of such problem is pages with similar words, right? Or customers who purchase similar products, right? So you want to find customers that are similar so that you can recommend an item that one of them buys to the other person, right? So it has some applications in recommender systems. And also finding images with similar features, things like that. There are many examples where we want to find similar things, right? Similar sets. Why is this a problem in high dimensional space? Well, for example, if you want to work with images, right? So an image is basically a two-dimensional vector, right? Where we have all of the pixels, right? So we have a value for every pixel. So you can basically convert that 2D structure to a vector, right? So the first row, second row, third row, so you can write all of them back to back, and you end up with a vector, right? So this vector, how many dimensions do I have here? 1, 2, 3, 4. So 9. I have 9 dimensions, right? And in reality, images have millions of pixels. So we will have millions of dimensions, right? Now, when we talk about similarity, we need to quantify it, right? What do you mean by two images are similar, right? Again, computers don't understand anything. You have to really give me a concrete method for quantifying how close they are. For now, let's suppose that we have a function like d that takes two vectors or images, and it tells us, or it quantifies the distance between these two images, x1 and x2. Okay, I'll talk about this function in a bit. What we want to do is to use this function, and we have a collection of many images, for example, right? What we want to do, we want to apply this function to every pair of images, right? And we want to figure out if the distance is less than some threshold s, then we call them near or similar, right? So that's the idea. And you know, in order to do that, the naive approach will require O of n squared operations, right? Because we need two loops, right, to generate all of the pairs of xi and xj's, right? And then we apply the function and see if the distance is less than threshold, right? So it's O of n squared. which is really bad for big data sets, right? N is in the order of millions, and then it's terrible. Today, I want to present a solution for this problem that solves it in O of n, which is crazy. Going from n squared to n is not straightforward at all. So if you know a solution without reading this topic, you are a genius. If you don't know a solution that can solve this problem in O of n, it's okay. It's fairly complex, and that's why we need a lecture to present the solution. Okay, finding similar items. So the first thing we need to do is to figure out what distance means, right? And I'm going to present a metric for quantifying the distance between two sets. It's called Jaccard similarity. It's very important, everyone. So make sure that you understand this, otherwise you don't understand anything in this lecture, okay? The Jaccard similarity is a metric to quantify the distance between two sets. It tells you how similar they are. How do we calculate it? It's very easy. I'm getting some feedback. I'm going to mute the microphone. Okay, so the Jaccard similarity of two sets, C1, C2, is defined as the size of the intersection, how many items are shared between these two sets, divided by the number of items in these two sets, so the size of union, right? To give you an example here, so I have two sets, right? So I'm visualizing them like this. So they have three common elements, okay? So what is the Jaccard similarity for these two sets? Well, it says the size of the intersection, right? So here we have three nodes that are shared. So it will be 3 divided by the size of the union, right? So how many items we have across these two sets? So 1, 2, 3, 4, 5, 6, 7, and 8. So the Jaccard similarity will be 3 over 8. As simple as that. We also define a similar metric called Jaccard distance, which is basically 1 minus Jaccard similarity. Okay. So if my Jaccard similarity is 3 over 8, the Jaccard distance is 5 over 8. Okay. I typically refer to Jaccard similarity in this lecture. Okay, let's make sure everybody is on board before we move on. Okay, I want to make sure everyone knows what Jaccard similarity is. Questions?
Hey, Professor. Good morning. So I just wanted to make sure so I'm not completely clear yet exactly what's going on. So the Jaccard dissimilarity is only defined for whole sets, right? Not individual points. Is that right?
Correct.
Okay.
And how similar two sets are.
And the intersection means that the elements are equal to each other, right?
Yes. Identical. So the elements that you find in both of them, right?
Right, but that's different than the distance thing, right? Because if 2 pixels are like very close to each other in value but not quite equal, that wouldn't actually make it into the Jaccard similarity, right?
Yeah. This is like the mathematical presentation, right? So when we say intersection, identical items, right?
Got it. Yeah. Alrighty. Cool.
Exactly. Yeah, the similarity is on the whole thing, right? On the two sets, not individual points. Individual points help us figure out what Jaccard similarity is. All right, let me check the chat to make sure there's nothing here. Okay, so I assume all of you know what Jaccard similarity is. It's pretty simple. I just wanted to make sure you know it because I'm going to say Jaccard similarity a million times today. So what I want to focus on in this lecture is not images, actually, it's documents, okay? So we have a large number of documents in the order of millions, and I want to find near duplicates, okay? Why do we care about this particular application is, for example, we want to find mirror websites or approximate mirrors, right? Why do we care about that? Because a search engine doesn't want to show both copies, right? So if you search for something, sometimes there are like mirror copies basically of a website, right? So there's another copy on another domain for some reason. The search engine doesn't want to show you duplicate results, right? So it wants to find, it needs to have a way to find which documents are duplicate or near duplicate to remove them from the search results. And also for news articles, you see when different news outlets talk about the story, those documents are very similar, right? So when you search for something in the news, search engines typically want to cluster them or group them, right? That, okay, all of these things are talking about the same thing, right? So we need to know a way to find similar documents. So these are examples of why we should care about finding near duplicate or similar documents, okay? So again, the problem is that we have many documents and we want to find similar ones. Like the image example, but here we are dealing with documents. So the problems that we have for this is that many small pieces of one document can appear out of order in another document, right? So it's not just a matter of directly comparing, it's sometimes more complicated. So too many documents, right, to compare all pairs. So n is big, in order of millions or billions. And these documents are can be so large that we cannot fit all of them in main memory. Okay, so these are some problems that we need to deal with. The algorithm that I'm going to talk about that achieves O of n in finding similar items is called the locality sensitive hashing. And that's basically, it's a 3-step algorithm, and the third step is also called locality sensitive hashing. So it can be a little bit confusing. So let me present the big picture first, and then I'll talk about every step. So first, we start from a bunch of documents, right? Millions and billions of documents. Usually when we work with like big data problems, the first step is to somehow represent that thing that we're working with, right? So how do you want to represent the documents? We use something called shingling. Shingling actually converts documents into a bunch of sets, okay? And then in the next step called minhashing, we take these sets and we create small integer signatures. So it's kind of a compression method. And finally, in the last step called locality sensitive hashing, we find candidate pairs. Okay, so this is an estimation algorithm. So it doesn't tell you for sure if these are similar, but it offers you candidate pairs that are similar with a very high probability. Okay, so that's the high level picture of what we want to do. All right, we start from a set of many documents and we want to find similar items. So I'm going to basically the layout of this lecture is basically talking about each of these steps. Let's start with the first step called shingling, and that's converting documents to sets. Okay, so we want to represent documents, right? We have done that before, right? If you remember, in the context of search, we said we can use the idea of bag of words, right? The bag of words idea is that it says, okay, we have a document, we throw away all the grammar and everything, and we just keep like what words we have, right? So you create a set from every document, right? Can we use that here? It turns out it's not a very good idea. And the reason is, for this application, we care about the ordering of words, right? We care about in what order these words appear in the document. And unfortunately, the bag of word idea throws away the ordering, right? It just keeps the words, right? No ordering is preserved. So we don't use that, but we use something very similar called shingles. And you already know this concept, right? It's a different name for something you already know. Shingles is same as k-gram, right? We talked about n-gram before when we talked about analyzing text, right? So it's basically a group of letters or words, right? And then it has a parameter like k or n that tells you how many words or letters you want to keep, basically, or keep track of. So the tokens can be here words or characters, okay? And here, let me explain this using an example. Suppose that k is 2 and my document only contains these letters. It's a very simple example to tell you what's going on. Okay, so this is all I have in my document. Now, if I want to apply kgram or shingle on this with k2, it's very simple. You consider a window with that length, and here, as I said, we care about 2 letters. Okay, it can also be words. So the first 2 letters is AB, so I add it to my set. The next 2 will be BC, right? So I add it to my set. The next one will be CA, right? So I take a window, right? And I slide it over the text, right? And I keep generating these tokens. And then the last one will be AB. Well, I have seen that already because remember, it's a set, right? So we don't keep duplicates. So we have already seen AB. So we keep sliding the window until we cover the entire document. And then when you are done, you end up with a set like this, right? These are the shingles of that document where k is 2. Makes sense? So it's exactly like n-gram, right? So we create all of these shingles that we have, right? And it creates a set. Now, another way to represent, so one way is to keep that set, right? For example, A, B, C, D, something like that, right? So another way to represent it is to convert it to vectors. How? So basically, if k is 2 again, right? What are the possible shingles, right? What like all possible shingles? So it starts from AA, right? And then AB, AC, right? It goes basically covers all of the A's, and then we start with B, right? BA, B, B, so on and so forth, and then it finishes with ZZ, right? So these are all possible shingles. Agree? Now, so technically, I can represent a document as a vector, the Boolean vector, that is something like this. And the length of this vector is the same as the number of tokens that I can have, right? Here, k is 2. If it's 3, it will be like AAA, right? Something like that. So what does this presentation tells me? It tells me, for example, if we consider the same order, it tells me that token AA doesn't appear in this document. Similarly, AB doesn't appear in this document, but AC appears in this document, right? So on and so forth. So you can also have this binary representation that every bit tells you if that token is in the document. Supposing that we have sorted all possible tokens, right? Like what I did from AA to ZZ, right? And this is where when k is 2. Okay. Why did we care about converting documents to sets? Well, we can use Jaccard similarity to find the similarity between 2 documents. That's why we converted it to a set. Okay, that's the idea. So the idea is documents that have lots of shingles in common have similar text. Okay, even if the text appears in different order. So that's the idea behind all of this, right? Now, we have to be careful, right, that k should be large enough. Otherwise, most documents will have all of the shingles, right? So if k is 2, it's probably useless, right? Because it will see that almost all documents have all the shingles. So in practice, k is chosen to be between 5 and 10 when we use letter shingles, okay? When we are working with word shingles, it's smaller, sorry. It's like 2 or 3. So when you work with letters, we typically look at a window that contains like 5 to 10 letters, right? And remember that this can go across words, right? So if the first word has 3 letters and then I have a space and then the next word. So when K is 10, it covers multiple words, right? And then I take that window again, slide it, come up with all of the shingles. That's it. Now, are we done? Okay, so we have converted documents to sets, right? And now we have a metric, Jaccard similarity. Are we done? Can we just find similar items? Well, no. Here's an example, right? So if n is 1 million, so if you have 1 million documents, we have these many comparisons that we have to do, right? Because we need a loop, 2 loops, right? Compare all of the documents, right? And we apply Jaccard similarity on the pair and then figure out if they are similar or not, right? And suppose that we can do 10 to 6 comparisons. So this is like 1 million comparisons, 10 million comparisons per second. That it would take 5 days to basically inspect all pairs. So that's not good. If n is bigger, if it's 10 million, it takes more than a year to look at all pairs. So that's why O of n squared is not good. Moving forward, okay, that was just a representation. It was not the solution. Okay, so we converted documents to sets, and now we want to basically apply another step that converts these sets into small signatures called Minhashing. So as I told you, a document can be represented using a binary vector or a binary number, basically, right? That indicates if we have a particular token in the document or not. Why is it a good idea to use binary? Well, because computers are good at bitwise operations, right? And you can easily calculate Jaccard similarity with a few bitwise operations, right? So, for example, you can, if you have 2 documents C1 and C2, you can calculate the bitwise and then count how many ones you have. That would be the size of the intersection, right? And then you can also take the bitwise OR and then count the number of ones. That would be the size of the union set, right? So it's a good idea to use binary, right? Now, every document is represented by a vector, a binary vector, right? So I can basically put these vectors side by side and they construct a matrix, right? So here is my document 1, document 2, document 3, and document 4, right? So I'm writing the vectors vertically, right? So this says, for example, I'm just making this up, that AA appears in document 1, appears in document 2 and 3, but not in document 4, right? AB appears in document 1, document 2, but not in 3, so on and so forth, right? So this is again, a small example. In practice, we have millions of columns, right? Because we have millions of documents. And then we have many, many rows, right? Because we have so many shingles, right? So for example, if K is 10, do you know how many rows we have? I think it's the permutation of English letters, right? So like for the first token, for the first letter, we have 21 choices, and then for the second one, we have 21 choices. So if we have 10 of these, right? So it will be 21 to 10. And that's a big number, right? So we will have so many rows, right? Because these are all possible tokens that we can have. Let me answer a few questions here. How do we get all possible shingles? It's basically you just need to compute all of the permutations. Okay. How do we do that efficiently? I'm not sure exactly what you mean, but we can, I think, construct them, right? To see the permutations that we have. Let me think more about it. Won't any decent size K lead to a shingle array that almost equivalent in size to the original document? Good point, right? So this is basically what I was actually driving here. So 21 to 10, that is a big number, right? So these many bits, right? Divide by 8, it will be bytes, right? So it will be like 2 and then 12 zeros in front of it. Good point, right? We have many rows here, right? That's why this is a very sparse matrix, right? There are so many possible shingles, but only some of them appear in every document, right? The other problem is it's a huge matrix and most of it is 0, actually. That's even more problematic, right? So hopefully these questions were nice. So I think we have good motivation for coming up with a technique that compresses this data structure. This matrix is just so big that we cannot use, right? Let's compress it. And before I move on, so suppose that, and let me clear the document. I have a question for you guys, just to make sure that you understand this concept before we move on. So let me erase all ink. So again, this is document 1, this is document 2, 3, and 4. Okay, so there is a poll. Please answer this. Don't answer in the chat. So let me launch it here. So the question I have from you is that suppose that this is the matrix that we have, right, for the shingles. And these are all the shingles. Let's suppose this is a simple example. Now, my question is, what is the Jaccard similarity of document 1 and 3? Can we figure out Jaccard similarity from this matrix? So the question, I think people of YouTube don't see this. So what I'm asking is, what is the similarity of document 1 and document 3? Most answers, so most of you answered 3/5. So let's see if it's correct. So Jaccard similarity is number of shared items divided by total number of items, right? So we are looking at document 1 and document 3. So we only care about these two columns, right? So number of shared items. So this one appears in both of them, right? And then this one appears in both, and then this one appears in both, right? So there are 3 common elements, right? Divided by total number of elements. So this one appears in at least one of them. This one appears at least in one of them, right? It appears in the first one, but not the third one. We don't care. We are taking the union, right? So we don't care. So, and then the here, here, and here, right? So there are 5 elements. 3 of them are common. So the Jaccard similarity of the document 1 and 3, or column 1 and 3, is 3/5. Any question about this? So the idea is, okay, cool. This data structure is nice. We can calculate Jaccard similarity, but as we just talked about this, it's such a big matrix, right, that we probably cannot use. Nice idea, but not practical, right? So we want to compress it. And here's another example for column 1 and 2. You can read it yourself. By the way, these slides have too much text, okay? But I explain everything, okay? They meant to be self-contained, so I may skip stuffs, but I don't really skip stuffs, okay? Let's just explaining stuffs in the slides. So we want to take this data structure, this matrix, and compress it, but we want to preserve something. We want to create these small signatures from the columns, right? But with the condition that the similarity of columns should be the same as similarity of signatures, meaning that in this compression procedure, we do not want to lose similarity, right? We just showed that we can use this matrix to calculate Jaccard similarity. I'm going to compress it. You should tell me, hey, be careful. Sure, compress it, but you should still be able to find Jaccard similarity, right? So again, high-level idea here, we can basically create some small signatures. I haven't told you how. I will. And then we can look at these pairs of signatures, right? But again, as you can see, this will be still O of n squared, right? I have compressed the data, right? The memory footprint is smaller now, but in terms of calculation, I still need to look at all pairs of signatures, right? For every document or every column, I came up with a signature, small signature. Now, I still need to compare them. So, okay, this was good, but it's not enough. And that's why we need the next last step, which is locality sensitive hashing. But let's talk about how we can compress, okay? So the idea is to hash each column to a small signature, H of C, okay? And the idea is that these signatures are small enough that they fit in memory, okay? And important thing that we need is that the similarity, the Jaccard similarity of two columns should be the same as the similarity of the signatures, right? So similarity of C1, C2 should be the same as the similarity of hash of C1, the signature of that column, and hash of the other column, right? So we need to preserve the similarity in this hashing procedure. So if we want to be more precise, what we mean is that if similarity of C1 and C2 is high, then with a high probability, we want their hashes to be the same. And if the similarity is low, then with the high probability, we want their hashes to be different. Not certainly, but with high probability, right? A suitable hash function that actually compresses data for us and preserves similarity is called Minhashing. I'm going to explain how Minhashing works. This is just a wall of text. It's just more efficient to teach you Minhashing using an example. So this is the matrix that we had from before, right? So different documents again, right? Document 1, document 2, document 3, document 4. And each bit tells me if that shingle appears in that document or not. Now, this is how Minhashing works. Again, the idea is to compress the data. And remember, we have many rows, right? In my simple example, I'm only showing like 7 rows. The Minhashing algorithm works like this. First, you come up with a permutation. What is this permutation? It's a reordering of the rows of this matrix. So you want to shuffle the rows in this matrix, okay? So that they appear in a different order. For example, here what I show is one sample permutation, which says in the new permutation, the new matrix, okay, this row will be the first row. This row will be the second row. This row will be the third row. This row will be the fourth row, so on and so forth. So I'm not showing you the result of this, so you should do this in your mind, okay? So we start from the matrix, we come up with the permutation, which is a different ordering of the rows of this matrix. Okay, now what should we do now? In order to find the signature of each column for this given permutation, you should do this. You should go to the first row. This is the first row here, right? After permutation, right? And now, for now, I'm calculating it for first column, okay, document 1. Do you see a 1? No. Continue. Go to the second row. Do you see a 1? Yes. Write down the row number in the new matrix. So I found a 1 in the second row. That is the signature of that column for that given permutation. I do this again for the second column. So I go to the first row, which is this. Do you see a 1? Yes, here in the first row we found a 1. So we write down the row number, row 1. So basically, the signature tells you what is the first row that has a 1, right? So you should inspect the rows in the permuted matrix and then see where you find the first 1. And that's the signature of that matrix. And you can do the same thing. So that will be the signature. So let me see if there's any question. So what is the purpose of permutation? So it's basically the implementation of the hashing idea. Because a hash function, in this case, what it does, it takes one column, right, and it gives us a number, right? So this is how it works. So a given hash function shuffles the row, right? It changes the orders, and then it tells you the row number that has the first 1. So it took the column and gave you a number. So that's a hashing.
I just wanted to ask that instead of like we reorder it, we could have had like a 1 5 1 5 kind of like just indexing that row.
Do you mean that? Okay.
Like,
do you mean do I actually shuffle the matrix?
yeah,
I
like
don't.
you know,
No,
the
I don't,
fifth,
because it's a lot of data, right? If that's what you mean. So we don't physically move data.
But why do we even do the permutation? Why can't we just use the matrix as is?
Because the matrix as is one of the permutations. And what we need is different permutations, as I will explain next. Okay, that's why we reorder the matrix and we redo this over and over again. I will explain that in a second. So it seems like without the permutation, the upper rows have a higher chance of being accepted. Yes. Also true for permuted matrix, right? Because it's more likely that you see something in the first rows. For example, here you can see, despite the permutation, I still end up with the small numbers, right? Because it's likely that I see something, I find something in one of the first rows. And now when you shuffle them, when you reorder them, you are kind of giving a chance to all rows to be selected, right? Otherwise, the rows at the bottom of the matrix have almost no chance to be selected. Very good questions. But now let me complete this, and hopefully it makes more sense then. So this was one permutation, and I came up with a number for every column, right? So every permutation gives me a number for every column. Now, I have another question. Is the permutation order randomly assigned? Yeah, sure. Now you can repeat this process with a different permutation. So you shuffle the rows again, okay? And now you repeat the procedure, all right? Same thing, right? For example, here, why is that one 4? Because, let's see why is that one 4. So it's the third column that we should look at, right? We go to the first row. it's a 0. You go to the second row, it's a 0. You go to the third row, it's a 0. You go to the fourth row, it's a 1. So we write 4. So basically, every time you have a new permutation, you end up with new numbers, right? Because it's randomly shuffling the rows, right? So a different row will be selected, right? So you can continue this and keep producing new rows for our signature matrix. That's a term that I will use, right? So the signature matrix is this compressed matrix that we create and build using the original matrix. Every row of the signature matrix is coming from a particular permutation. Every column of the signature matrix is a document. So here, if I have n documents, my signature matrix will also have n documents, right? But I will probably have much fewer rows, right? So how many permutations should we have? It depends. You will see later. It's one of the tuning parameters, okay? But we can have as many as we want, okay? But not too many, because then it becomes the same as the original matrix. But as we talked about this, the original matrix has many, many rows, right? So even if we do calculate this for like 100 permutations, it's nothing. We have a question. Umaid, go ahead.
Professor, I was getting pretty confused as, well, I mean, if we want the signature matrix to compress, but I mean, I don't completely understand how are we compressing it over here. Like, we still need to know that what's the order of this, the, for example, the first one, there's 2 1 2 1, and we should know that what order are we talking about, so we need to save that as well. I don't know if I'm on the right track.
Okay.
All right. What's on here?
Okay, so after you use your permutation to calculate the numbers, the signatures, you don't need that permutation anymore. All I care is the numbers that I have in my signature matrix. So I do not need to store these things after I'm done with the calculation. So remember, here we just calculated. When k is 10, this we have 16 times 10 to 12 rows, right? And then here, oh, what's going on? Okay, sorry. So many rows here, right? But here you're reducing it to, let's say, 50, 100, something much smaller, okay? That's the idea. And then the idea is, okay, we forget about the original matrix. That was like, the matrix was too big, right, for calculation and computation. So we forget about that. And the idea is we want to use the signature matrix to calculate similarities, right? If you remember, we said we want to compress, but we want to preserve similarity, right? So moving forward, how can we use the signature matrix to calculate similarity? Well, there's this theorem, right? And we have a proof for it here that says the similarity of two documents or two columns, C1, C2, is the same as the probability of the hashes to be the same. So for example, there are two columns like C1, C2, right? For a given permutation like pi, right, it says the Jaccard similarity of these two is the same as the probability of the numbers that I come up with using permutation pi being the same, right? For example, both of them are 2, both of them are 4, right? So there's a probability assigned to that, right? The theorem says that probability is the same as Jaccard similarity. And that's how the signature matrix preserves the notion of similarity. We can still calculate similarity without using the original matrix, but rather the small matrix. That's good. In why that's the case, you can read this. Pretty straightforward. Moving forward, what does it mean? Okay, so again, let me explain this using an example. What do you mean? Explain. Okay, so we have the original matrix, permutations, we came up with the signature matrix. Okay, now how can we use the signature matrix? First, let's look at Jaccard similarity. Now you master this, right? So you can look at like two columns here and tell me the Jaccard similarity. For example, here, column 1 and 3. So this one and this one. Let's quickly calculate Jaccard similarity. Okay, so 1, 2, 3. So it's 3 over, and then 1, 2, 3, 4. So the Jaccard similarity is 0.75 for 1 and 3. Hopefully you agree. Now, okay, now forget about the original matrix. We don't have that. I only give you the signature matrix. Can you estimate the similarity from the signature matrix? Well, you told me that the Jaccard similarity is the same as the probability that two columns match, right? So here I have some instances, in this case only 3 instances. From that I can calculate Jaccard similarity or estimate it. How does that work? And I will explain that more in a second, but let me show how it's calculated first, and then I tell you what's behind it. So in order to calculate Jaccard similarity from the signature matrix, you count how many, so again, we are talking about document 1 and 3 here, right? So how many rows match? So this row match, both of them are 2. This one doesn't, right? So we have a check mark, X, and here another check mark, right? It says it's the number of check marks, the number of rows that we have a match. Oh, sorry. 2 over all row divided by total number of rows, 3, 2/3, or 0.67. So that's our approximation. Actually, pretty close to the ground truth, which is the actual Jaccard similarity, right? So that's the idea. How does it work? Okay, so let me explain why it works. Why do you calculate it like this? If I go back, if you believe that that's true, how can we actually calculate it? Why did I calculate it that way? Look, let me give you an example. Suppose that we have a biased coin, okay, which means that when you flip the coin, it will be heads with probability X and tails with probability 1 minus X, and X is not 0.5. Okay, we don't know what is the probability. It's a biased coin. Okay, it might be like 40% heads, 60% tails. Okay, we don't know that. We don't know that. We want to figure out, we want to estimate what X is by doing experiments. Okay, so I tell you this, I flip the coin 100 times. Okay, and in 61%, or like in 61 cases, right? I did this 100 times. In 61 cases, it was heads, and in 39 cases, I saw tails. Right? From this experiment, if I ask you, what is the probability of seeing heads when we flip the coin? What is your answer? What is the probability of seeing heads when we flip a coin? So I did an experiment before. I flipped the coin 100 times. I saw heads 61 times. I saw tails 39 times. Do you agree that our best guess is that the probability of heads is 0.61, right? Or around 60%, right? Because from our experiments, in like 61% of the time, we saw heads. right? So from the experiments, that's the guess, right? So you calculated probability from some trials, from some instances of the coin flip, right? This is exactly what we are doing. We need to calculate the probability of hashes being the same. The way I estimate it is by doing some experiments. Each row, each permutation is one experiment, right? So here, when I see 2 2s, that's not the probability. That's an instance, right? So I flip the coin, and it happened to be the same, right? Again, I flip the coin this time, they were different, right? So each permutation gives me one instance. So it's like my 100 times trying to flip the coin, right? So that's why I'm saying it's like the story of flipping coins. So I test this, right, using different permutations. And every time, with some probability, something happens, right? And then I use those instances to estimate what the probability was. Obviously, I might have some errors, right? As you can see, this was not exactly the same number, but it was fairly close, right? And if you want to increase your accuracy, you should increase the number of rows, right? As you increase the number of rows, it gives you a better estimate, but at the cost of a bigger signature matrix, right? So there's a trade-off. So that's the idea behind it. And so that's the idea, and that's how you calculate it. So you look at how many rows have the same numbers, divided by the total number of rows in the signature matrix, and there you go. That's your estimated similarity using the signature matrix. Okay, which turns out to be very close to ground truth, which is calculating Jaccard similarity on the original matrix. Any questions before we move on? While you think or type your question, let's take a step back, see where we are. Okay, things are getting complex. So this is a multi-step algorithm. The idea is we have a lot of documents. We want to find similar documents. In the first step, we came up with the shingles, right? We converted documents to sets. And in this step, Minhashing, we are creating a small signatures from the huge input matrix that we had from the first step. We are not done yet. We have another step that finds similar items. How do we know how many permutations? It's basically an optimization parameter. At the end of this lecture, I will talk about it if I have time. So the signature matrix is a small, right? So for example, if we have 100 permutations, right, the size of the signature for every document will be around 100 bytes, right? Which is much better than 2 times 10 to the power of 12 bytes. So we have compressed it, and it preserves similarity. So that's really nice. And this is a trick for implementing it, because when I said permutation, it means that we change the order of rows. If you want to do that, it's a huge matrix, right? We said it's difficult to work with. So how do you want to reorder the rows? It's very difficult, right? So in practice, we don't actually move the rows physically, but we use a trick to do this. So it gives us the same exact results without actually physically moving the rows, okay? And this is something optional for you. If you want, you can read it and you can follow an example. It's pretty straightforward. And that takes us to the last step, which is locality sensitive hashing. One question before we move on. How do we ensure the randomness? Does this conclusion come from large amount of experiments? Correct. As you know, you really approach the ground truth if you have many samples, right? This is this the law of large numbers? I confuse it with another one. I think it is. So but we don't want to have many rows, right? Because again, we don't want to make the signature matrix too big again, right? Because that was the whole purpose of this. So there's a balance. I will talk about this, okay? So you don't need many per se. Something like 100 is probably more than enough to give you an idea of what order I'm talking about. And yes, the random, it should be really random in order to conclude all of these things, right? So that the trials are independent. If you're familiar with the statistics and probability, it's like flipping the coin is like a Bernoulli trials. The trial should be independent, right, from each other in order for all of those things to make sense. And if I want to bring that into our problem, it means that our permutations should be random. Good questions. Let's move on to the last step to see how we find candidate pairs. What are candidate pairs? So as we said, this is an estimation algorithm, and it tells us some candidate pairs. It says that it looks like these two documents are very similar, okay? So I know that they are similar with a high probability, but I'm not 100% sure. So if you really want to be sure, you should look at the original matrix to figure this out, okay? But I will show you that the accuracy is actually very high. And the idea is using hashing again in this step, and I will use an example to show you how it works. But before we move on to locality sensitive hashing, it tells you, this slide tells you how you can actually use the signature matrix to come up with candidate pairs, okay? So we have a threshold S, right? Our job is to find the documents that are similar, right, with the Jaccard similarity of S or higher than S. Okay, so S can be 0.8. You're supposed to find all of the documents that have a similarity higher than 0.8. Okay, how can we do that from the signature matrix? Well, you know that, right? So for example, if you want to do this for column 1 and 3, so okay, they're different here, they're the same. So like 2/3 is our estimation, right? So we believe that similarity is around 2/3. Now I compare that with my threshold. If it's more than that threshold, I select that as a candidate pair. If it's under that threshold, I ignore it, okay? But the question is, does this help? No, because this is still O of n squared, right? Because I have to compare the signature of all columns, right? Again, two loops, right? Create all of the pairs, right? And then check to see if they're a candidate pair or not. Okay, so I couldn't solve the O of n squared problem. That's why we use locality sensitive hashing. What it does, it actually hashes columns to different buckets, okay? And the idea is, if two columns are identical, they will be hashed to the same bucket. The hash function produces the same value, output value, right? And it makes sense. So hash functions are random, right? But for a given input, they always produce the same output, right? So if you give them X a million times, they produce the same output a million times, okay? So if two columns are the same, they should be hashed to the same bucket or the same output. That's the idea. But I will explain how it works exactly. The locality sensitive hashing works like this. It takes the signature matrix, so something that we came up with, right? So the signature matrix, and it divides it. So here the big box is the signature matrix. It divides it into a bunch of bands, okay? So they group the rows into some bands, okay? For example, it says the first 5 rows are a band, and then the next 5, so on and so forth. Okay, so the parameter that we have is R. R is the number of rows in every band. So for example, here we can say 5, right? And then if we have 100 permutations, so we have 100 rows, right? So B, how many bands we have? So 5, so it will be 20, right? So you can divide your rows into 20 bands, each has 5 rows, okay? And then you hash rows. Let me show you an example. This is one row, agree? It contains like 5 rows, for example. Like it's these, I'll talk about these parameters later. For now, let's suppose it's 5. So I look at those 5 rows, okay? So what do I have here? So 5 numbers for every column, right? For example, 1, oh, I cannot see it. So it's 1, 4, I don't know, 3, I don't know, 3 again, right? So, and then I need another one, let's say 2. I said 5 rows, right? So for every column in that row, you have 5 numbers, right? So these are coming from 5 permutations. And there are other bands. I'm explaining what I do for every band, and I will repeat this. So for every band, we hash those numbers, right? 2, 1, 4, 3, 3 for that first document. Second document will have some other numbers. The third one has some other numbers. We hash them to different buckets, okay? Here it says, as you can see, document 2 and document 3, 4, 5, 6, they hash to the same bucket, right? We are saying that they are probably identical. So I consider them to be candidate pairs. What do I say probably and not definitely? So they hash to the same bucket. I'm saying they are probably identical. Why is that?
At different orders?
No, if like ordering is important, right? So like the vector 2, 1, 4 is different from 4, 1, 2. Collision, right? Like you have a few answers here, collision, right? So it's possible in hash functions that 2 different inputs like x and y both be hashed to the same value, right? That's called hash collision. That's possible, right? So that's something I have to keep in mind. I have to talk about that. So for now, let's assume that when 2 documents are hashed to the same bucket, we call them candidate pair. And I repeat this procedure for all rows. And here, columns 6 and 7 are hashed to different buckets. So we are saying they are surely different. Okay. And I repeat this process for every row. So sorry, for every band. Okay. So if I have 20 bands, I repeat this procedure. And in order to say 2 documents are candidate pairs, it only takes 1 iteration. Okay, so if in one iteration they are hashed to the same bucket, we call them candidate pair, even if that doesn't happen for other rows. Okay, so 1 band is enough. 1 band is enough. As soon as they are hashed to the same bucket in 1 band, they are a candidate pair. Okay. There are details, obviously. We should have enough buckets. If we don't have enough buckets, the probability of a collision goes up, right? So we assume that we have enough buckets. So that's another parameter we need to engineer to make sure collision is minimized. After that, if we assume that that's fine, then we assume that when 2 things are hashed to the same bucket, they are identical. And we are not worried about that. Why? Because we can actually double check this, right? So when the algorithm tells me that document 1 and 3 are candidate pairs, right? This might be because of collision. They are not really the same, right? But it was because of a collision. So I can go back to the signature matrix and double check their signature matrix to see if they are really identical or not, right? So this is a false positive. Can be a false positive, meaning that 2 things are not the same, but they hash to the same bucket. So we have a verification mechanism. We can check the signature matrix to make sure that they are really identical. So we're not too worried about it, okay? But we engineer the number of buckets in a way that hash collision is minimized. Okay. We have some examples here. So suppose that we have like 100,000 columns or documents, right? 100K documents, signature of 100 integers. So we have 100 rows. So we did 100 permutations. So the signature will be like 40 megabyte. That's good. And that should be capital B, Stanford. Or no, maybe it's really bit. I'm mistaken, probably. So, let's say we choose B to be 20 and R to be 5. Okay, we need to divide these 100 rows to 20 rows, and these are just random numbers. Okay, I'm just going to tell you how it works, and I will talk about the numbers in a second. And the threshold is 0.8. Okay, so if two documents have a similarity of 0.8 or higher, they should be identified as similar items. With these numbers, let's see how it works. Okay, so in the first example, I assume that the similarity of two documents is really 0.8. So it's exactly at the threshold. This is the most challenging case. Okay, so the similarity is exactly 0.8. So it is at the threshold, so it should be identified. They should be identified as candidate pairs, right? What is the condition that they are identified as candidate pairs? Well, at least they should be common. They should be hashed to a common bucket, right? In one of the bands. So let's calculate the probability. So from the theorem, I know that two numbers for a particular row match with the probability that the same as the Jaccard similarity, right? So I see two identical numbers with probability 0.8 because I know that the similarity is 0.8. So now what is the probability that we have a match in a band that has 5 rows? So the probability that the first two numbers match is 0.8. The probability that the second two numbers match is 0.8 again, so on and so forth. So it's like 0.8 times 0.8 times 0.8, 5 times. So it's 0.8 to the 5. And it's like 32%, 33%. So this is the probability that they are the same in one band, 33%. Probability that they are not similar in any of the bands, okay? That would be 1 minus that number, right? We have like 70% chance that they are different, right? Raise that to the power of 20, that would be the probability that they are different in all 20 bands. It will be this a small number. That's a probability that I don't select them as candidate pairs, right? Because I calculated the probability that they are not hashed to the same bucket in any of the rows. As soon as they are hashed to the same bucket in one of the rows, it's fine. So that would be 1 minus this number. And that's like 99.9%. We truly identify similar items. So that's really good because it was a tricky case. It was 0.8. So if the similarity is actually higher than the threshold, we have a better chance to identify them, right? It becomes easier to identify them. So that's a small number. That's false negative, right? That means the documents are really similar, but we don't select them as candidate pair, right? So this is false negative. That's bad. If you miss something in this algorithm, there's no way to retrieve it, right? But as you can see, it's a very small number, right? That something is similar, two documents are really similar, but the locality sensitive hashing says they are not similar. They are not candidate pairs. So that's false negative, but as you can see, it's very low. Now, a similar example, but this time the similarity is 0.3, so it's way lower than the threshold, right? So they should not be selected as candidate pair. Let's calculate the probability. So it will be 0.3 to the 5. That's the probability of having identical bands, right? And then this part will be the probability that they don't match in any of the 20 bands, right? And then 1 minus that number will be the probability that we actually select them. So they are actually hashed, at least in one bucket. So this is the probability, which is around 4.7, 5% chance that two documents that are not similar, right? Their similarity is much lower than the threshold, are selected as candidate pair. This is called false positive. And as I said before, false positives are not very problematic because we can double check, make sure in the original matrix, double check to see if they're really similar or not. So that's fine. Or sorry, I mean in the signature matrix, I can just double check to see if they are really the same or not. Okay. So we're out of time. I'm going to wrap up this in a few minutes, so that might be best instead of continuing this next time. So we are done, except that I talked about some numbers. So let's see how we can pick these numbers. We are a bunch of things. Number of rows. How many permutations do you have? How many bands do you have? These are things that we need to answer. So this is the ideal plot for similarity versus probability of sharing a bucket. So it says if this is the threshold, right? If the similarity is lower than threshold, there should be 0 probability that they share a common bucket, right? And as soon as we pass the threshold, they should share a bucket with 100% chance. This is the ideal case, right? You can never achieve this, but this is a reference for us to see where we are, okay? So if we only have one band, one row, okay? So if you have one permutation, basically, how does this line look like? It looks like this, right? Because we know that if you only have one row, so we have only one pair of numbers, right? The probability of these two numbers being the same or sharing the same bucket is the same as their Jaccard similarity. This is the original theorem that we talked about early on, right? So it will be a flat line. They are the same, right? Very bad, very different from this line that we want to achieve, right? That's why we use the idea of multiple rows and multiple bands. So this is the parametric calculation of probabilities. So it's exactly the same as the numbers that I went over, but this is the parametric version of it. Just to show you how it looks like. In general, if you use B bands and R rows in every band, this plot looks like this. Okay, and for a given B and R, the threshold is better to be S. Okay, it's typically the other way around, right? We are usually given the threshold and then we try to find the parameters in a way that it looks nice. But it tells you for a given B and R, at what point the plot goes up, right? So if I know that my threshold should be over here, right? For example, 0.8, I can adjust B and R, right? So B times R is the number of permutations that you have, right? So basically you can change the number of permutations and or a number of bands or rows to adjust this line. So if you change these numbers, you will see that this line changes. When you increase your permutations, the line goes up fast, like crazy. Okay, so as you have more and more permutations, it looks more like a step function. That's the first thing you need to know. Okay, the second one is the location at which the line goes up. That can be adjusted by changing B or R, right? These are dependent, right? Because B times R is M, the number of permutations. So you can change these parameters so that the plot is moved to around where the threshold should be, okay? And this formula tells you for a given B and R or M where the threshold will be. So you can change them to get a nice fit. Now, in practice, you won't exactly get that step function, but something like the blue line, right? You can adjust it to be closer to the line, but at the end of the day, in theory, you have a little bit of gap here, right? and a little bit of gap here, right? So let's see what they are. This area, the green area, is false positive. Why? Because the similarity is lower than the threshold, so they should not be identified as candidate pairs. But unfortunately, there is a positive probability that we pick those pairs as candidate pairs. So it's a false positive, right? It was not supposed to happen, but it happened, right? And we have that region, that's false negative region. Why? Because the probability, the similarity is higher than threshold, right? Meaning that they should be identified with 100% chance, right? But unfortunately, it is not 1, right? It's like 90%. So this area, the blue area, will be the false negative ones, the ones that we miss. These are problematic, right? So if we miss something, we cannot recover them. False positive, the green area is okay. So when you adjust the plot, it's better to minimize the blue portion. The green portion can be fixed because we can double check to make sure, because false positive, it claims that they are pairs, right? I can double check to see, it claims they are candidate pairs. I can double check to make sure they are really candidate pairs or not. But if we miss something, if it doesn't tell me a pair exists, then there's no way I know about them, right? So we want to really minimize the blue area. So to summarize, we have a 3-step algorithm. There are a bunch of parameters we need to optimize to get to the thresholds that we care about, because whenever we solve a problem, we are given some restrictions that, for example, our false negatives should not be more than 1% or something like that. When we are given all of those requirements for a problem, we can adjust basically all of these parameters in order to achieve the required false positive, false negative, or if there are other metrics to basically solve the problem. And that wraps up this lecture. Questions? Sorry, we went over time a little bit. Next term, we go back to classroom and we will have our 1 hour 20 minutes. For some reason, my schedule says 1 hour 30 minutes, but it was a long time ago, but I remember the lectures were 1 hour 20 minutes, not 1 hour 30 minutes. I don't know why that was the schedule that was given to me. All right. But for online learning, I typically target 1 hour. So sometimes I have too much stuff, so I need to use more time. Okay, it looks like there's no questions, so I'm going to stop recording and I will be around a little bit longer. Goodbye to the people of YouTube. Goodbye.